theme for this year, with the theme for this year's celebration of Chemists Celebrate Earth Week being glaciers, hot topic, and cool chemistry. And in this special issue, they brought out a number of articles. 2 or 3 of them are actually simple experiments focused on the K to 12, that is the high school and the middle school and even the elementary school students. And based on those experiments, actually, our chair of our section, local section, Veronica, who is right here with us, she has actually demonstrated one experiment there in the science fair that was organized by the city of Los Angeles. And that was a very interesting experiment, and which I think a lot of school teachers can try in their own labs. And to mention about that, celebrating chemistry with the glaciers, hot topic, and cool chemistry, that was the heading of the very first article. And it mentions celebrate the International Year of Glacier Preservation and glaciers' role in creating a more sustainable world during April 21-27. So it is more focused on creating a sustainable world. And I'm sure all of us know what is the meaning of the word sustainable. And let me introduce our speaker today, Professor Claire Todd of UC, University of California, San Bernardino. She has graduated from the Pomona College and the Claremont McKenna College in geology in 2005, 2000, I should say, May 2005. Then she did her master's from Columbia University and then PhD from the University of Washington in Seattle, Washington State. And she worked as a faculty member at the Pacific Lutheran University in Tacoma, Washington until 2021, from which time she is a faculty member and chair of the Geological Sciences at California State University, San Bernardino. I had the occasion to read through a couple of her publications. One is some sort of a review article, Cryoscopic Sciences, Perspectives on Integrated, Coordinated, Open Network Science. They call it the ICON Science. And that was a very beautiful article. And it was followed in 2022 by another article which she wrote along with some other co-authors in the American Journal of Science in 2019, which was a beautiful, exhaustive review. And it was 30 or 32 pages. And by skimming through that, I found a section in which she mentioned about the experimental or the analytical techniques that she has used. And it very much heartened me to read through that because it is all chemistry. So geology and chemistry, they are not different, they are not far. So I know that already, but that made me get reassured about the fact that geologists also deal with a whole lot of chemistry. I don't want to go into details about the meaning of the term nuclide and all that, because I'm sure she's going to explain that to you. So the title of her seminar today will be Tracking Ice Sheet Retreat Using Cosmogenic Nuclides. Over to you, Claire.
Thank you so much. It's a wonderful introduction. Thank you, Krishna. And thanks everyone for being here. And for those of you who are watching it as a recording later, it's nice to have an opportunity to share my work and the work of others that I collaborate with. And yeah, to celebrate Earth Week and in particular the cryospheric part of Earth. So today I'll be talking to you about work that I've done since I was a PhD student, basically studying ice sheet retreat in Antarctica using cosmogenic nuclides. So this is a picture of my 2 students. This was taken in 2024, January 2024. And we have an undergraduate student, Karina Ramirez, and a master's student, Jacob Baker. And this is on our most recent field season to Antarctica. But I'll be showing you pictures from many seasons, a total of 6 seasons, just to give you an idea of the type of work that we do using cosmogenic nuclides. So I put an asterisk after my name just to point out that actually research happens in collaboration. So it's far from my own work. It's the work of myself and many other scientists and students. So you can see Jacob and Karina in those bottom 3 photos. But also I work with Greg Balco at the Berkeley Geochronology Center, as well as others across the United States. And also that all of this work is funded by the National Science Foundation. So all of the Antarctic research that I've done has been funded by the Office of Polar Programs, with the most recent award number included down there in the lower right corner. So what am I going to talk about today? I'll give you an introduction to Antarctica, tell you how we actually get there, and then show you some images to give you an idea about the kinds of geologic work, and then how we can pair those geologic observations with cosmogenic nuclides to get a history of the Antarctic ice sheet, and then bring it all together at the end for what we can learn from these observations of long-term ice sheet retreat. In this image in the background, we are hiking from a field area back to snowmobiles, which we will take back to our camp. So you may have read about Antarctica in the news over the past few years, often describing melting, that melting ice sheets are something that affects people around the world. And this has been going on for a few years, if not a couple of decades, renewed kind of interest in the rate of ice sheet retreat in Antarctica. And so I want to give you a little bit of background about kind of the scale and the processes that govern Antarctic ice sheet retreat. So first of all, a point of clarification, Antarctica is at the South Pole. So the South Pole, 90 degrees, is at 90 degrees south, and it is distinct from the Arctic. So the Arctic is at the North Pole. There's no continent in the Arctic. It's the Arctic Ocean that's covered by sea ice. But Antarctica is a full-size continent. In fact, if I were to get in my car here in San Bernardino and drive across to my hometown of Atlanta, Georgia, that would be roughly the distance from one coast of Antarctica to the other. And the surface area, the area of Antarctica, is roughly equivalent to the area of the United States. So it's a full-size continent at the bottom of the globe. And this is an image of me at the South Pole many years ago now, at the geographic South Pole, which is also noted at this dot in the middle of the image from the Southern Hemisphere. And the key thing about Antarctica is it is a continent, but it's a continent completely overrun by ice. It's divided into 2 ice sheets, an East Antarctic ice sheet, which is larger than its neighbor, the West Antarctic ice sheet. And those ice sheets are separated by a mountain range known as the Transantarctic Mountains. Less than 1% of Antarctica is exposed rock, but as a geologist, I have to go to the locations of exposed rock. So you'll notice that the field sites where I have worked are along that spine, those Transantarctic Mountains that divide East Antarctica from West Antarctica. And you can tell by the color scale that we have very thick ice in the center of these ice sheets, in particular in East Antarctica, which is well over 3,000 meters, approaching 4 kilometers thick of ice. It matters because we have those kilometers of ice thickness, again, approaching 4 kilometers thickness of ice. And that ice is actually grounded or resting on a continent that is below sea level. So on the left-hand side, you'll see that ice thickness, that deep dark red color, that's where ice is very thick. And on the larger map, those light blue to dark blue colors are showing areas where the continent is approaching 2 kilometers below sea level. So we have basically a shape of ice where about half of it is below sea level and the other half is above sea level. And that means that it's a potential vulnerability. We have all of this ice resting in a below sea level basin, and that can actually lead to a vulnerability and to a positive feedback where we actually get more melting. So let's think about that a little bit more. in this cartoon created by NASA, you see basically a cartoon of our ice sheet here, where part of it at the base is below sea level. It's resting or grounded on bedrock beneath, colored in brown here. And we have an ocean that's circulating up against where the grounded ice ends and floating ice begins. And so that actually can introduce warming to the edge of the ice sheet and potentially allow the encroachment of warm ocean water below the ice sheet. And so that can then kind of accelerate melt, accelerate flow. And it has the potential for significant global sea level rise. In fact, it's already contributing to sea level rise and has in the past as well. And so this matters because we are already seeing significant coastal flooding. So the National Oceanic and Atmospheric Administration has a really clever tool where you can view the impacts of sea level rise. And one of those is just showing simply high tide flooding that's happening today. So here in Southern California, for example, the dark red areas are showing areas that experience coastal flooding now. And of course, as you raise sea level, those areas are going to expand in size, but also the depth of the water will increase in areas currently flooded. If you go actually to the sea level rise viewer, you could play around and raise sea level. It's a wonderful interface. And then if you look at in the Bay Area as well, there's significant vulnerability in the South Bay and in the North Bay as well. And on this image here to the left, you can see where at a beach, they've basically posted where sea level will be in the future. So many communities are coastal around the world, and those low-lying areas are threatened by ice sheet melt and rising sea level as a result of ice sheet melting. So in short, there are ways in which Antarctica, however far it may be from our day-to-day lives, is actually posing a hazard, a risk to our future. And so what, as geologists, we ask ourselves is, how is the past, how is what has happened to the past connected to or related to what might happen in the future? In fact, geologists study the past in order to understand and predict future occurrences. And so we as geologists are thinking about, well, what is that long-term ice sheet retreat history? If Antarctica is retreating now, has it always retreated? How quickly has ice thinned or melted in Antarctica? So fundamentally, when we go to Antarctica, these studies, we're asking about the history of ice sheet change. And so if we want to know the history of Antarctica, we are going to basically go to those exposed rock areas to find out when and where the ice sheet was thicker. So in this image here, you're seeing one of our field camps that we established in the Pensacola Mountains in Antarctica. The pyramidal tall yellow tents are where people sleep, and the long orange tent in the background is one of our cook tents. So if you want to go to Antarctica, here's what you do. You catch a plane from Los Angeles. This is my student team the last time in the Los Angeles airport. And you fly to a country called New Zealand. And in New Zealand, you board another plane after getting some cold weather gear and checking in with the U.S. Antarctic program in New Zealand. And then you take off in a military plane from New Zealand to Antarctica. So you can see in this lower, the image on the left here, that is a screenshot that my husband took of a flight radar app showing our flight actually leaving New Zealand and flying south to Antarctica. So that is the plane that we were on. Here's a picture of it before we boarded the plane. And then inside the plane, it is a military style plane. It has basically netting seats that we sit in. And when you travel farther and farther south toward the Antarctic continent, you pass over open water, and then eventually water that is completely frozen, covered by sea ice. And then eventually you reach the continent where you're seeing mountains that are poking up through thick ice. Here's where you land on basically an ice shelf in Antarctica. And your first stop as a scientist in Antarctica is McMurdo Station. It is a research station. It's located here in the red star in the image on the right-hand side. And this is the very, very approximate flight path that we took to get there. McMurdo is a town dedicated to supporting science, run by the U.S. Antarctic program, which is funded by the National Science Foundation. And it has all of the things that scientists need to get equipped to begin their fieldwork. So the other interesting thing, this in the background here is McMurdo Sound, and it is completely iced over. So by the end of the season, that ice has broken up and has melted out, and there's a lot more wildlife and open water behind the station. We do a lot of expedition preparations in Antarctica. So you can see we do basically a practice trip with all of our snowmobiles and our gear. We spend some time planning out communications and emergency procedures. We practice crevasse rescue and glacier travel. We practice emergency radio communications. We pack up all of our food. So you spend at least a couple of weeks in McMurdo getting everything ready. And then we get back into a military plane to get to our field site. So you can see this plane has skis, and we're heading off to our field camp, depending on where it is in Antarctica. Depends on that determines what kind of plane you take. And here's my last research team. On the left is us getting started to go, and then about 5 minutes later, everyone was asleep but me. And then we touched down at our field camp. So again, we're going to areas in mostly the interior of the continent, where there are mountains, but it's mostly surrounded by just flat white ice sheet. So this is us unpacking all of our gear. Depending on the plane, sort of determines how you accomplish that. And we eventually set up our field camp, and the plane leaves us, and we're there anywhere from 2 weeks to 4 weeks, living out of these tents to prepare for our field camp, to prepare for our field work. So we have a cook tent where all of our food preparation happens, and eventually we are ready to go. So this is our most recent field site, and you can see these mountains sticking up in the background. These are nunataks. That is the word for basically mountains surrounded by ice. And they are places where geologists go in Antarctica to look for evidence of past ice sheet activity. So we use snowmobiles to get around. We make our own little gas station, if you will, to fuel our travels, and off we go. So the next few sets of slides, I'm just going to ask you to think about what you see. I'm convinced that any of you on this call or watching this video later could do what we do, which is open your eyes and make observations to the sites around you. So just looking at this image, anyone, if you want to put in the chat, or if you just want to unmute and say something, what do you see in this photograph? Yes. Okay, nice. Thanks, Mason. So I see some very smooth rock. Okay, piece of evidence number one, right? It looks like somebody took a piece of sandpaper to that rock. It's it's very smooth. It's almost shining in the light. It's almost polished. So great observation. What's another observation?
Seems to be a smooth ground there on which the rocks are there.
Yeah. Yeah, that's right. So even in the background, right, everything looks like it's been sort of mown over, kind of smoothed over, and then rocks piled on top.
Yeah.
Yeah. In many areas in Antarctica, not every area, but we're often some of the first people to be there. It's certainly low trafficked areas. And you can see these rocks are perched on top of each other. And that happens because ice basically evaporates or melts and lowers rocks on top of other rocks. So we call these perched or stranded rocks. That is the ice doing its thing, that we did not stack these rocks. And you can also see scratches on the surface of the rock. Those are known as striations. And that's basically occurs when you have rock frozen into the bottom of the glacier. And as the glacier flows over the mountain, it leaves all of these marks. In fact, if you look at these striations, you can see there has been a change in ice flow. That actually ice flowed one direction for a period of time and then shifted and flowed another direction. So the gradient of the ice actually changed, and the direction in which the ice flowed changed as well. Okay, next question. Actually, not yet. Soon another question. This one's a little hard to see, so I don't like to make too much out of this one. But in the event, hopefully the color on your monitor is good enough to see that there is actually kind of a bathtub line. It's a gray, basically kind of a gray, less weathered material, and then it's overlain on top of red, more weathered material. And that is evidence that basically it's kind of like a beach, that the ice reached an elevation and then left a lot of rock there and thinned or retreated away from that elevation. But likely in its most recent advance, it did not flow over the mountain because there's more weathered, oxidized material above it. And this line here is about 200 meters above the current ice surface. And we interpret this as evidence of a much larger ice sheet. Here's another image. So this rock, if you were to sort of look at it and its surrounding environment, it stands out. It doesn't fit, it doesn't match the surrounding bedrock. And so we describe these rocks as erratic. They're glacial erratics. They have been left behind, transported from someplace with a different lithology, a different rock type, and then deposited at the top of a hill as the ice retreated away from that location. So more evidence that the ice sheet was bigger in the past. And we also see these linear features of rock. Again, kind of like a beach, a high tide line or something, where you have a concentration of material in a linear feature, like a former ice sheet boundary. And these rocks look glacially transported. So their edges are rounded. They have smooth sides. Those are all evidence of glacial transport. We call these linear features glacial moraines. So here we have basically a colleague of mine standing at the peak of a ridge of material left behind by flowing ice. And all of this we interpret as the elevation of a past higher, thicker ice sheet. And these features, then, if you map them in a region, in a wider, broader area, you can sort of reconstruct where the ice sheet was in the past. And so in some places, we have what's called a drift. It's not a linear feature. It's simply just a field of stranded rocks that do not match the underlying bedrock lithology. So here we have almost a rock garden of sorts of rounded edged rocks stranded way above where the ice sheet is today. So how does this work? Can we actually use these deposits to answer our research question about the history of the Antarctic ice sheet and about Antarctic response to past changes? So first thing that has to happen is that glacier ice flows over and erodes the bedrock beneath. So ice actually has the ability to entrain rock, and then when it flows over other rock, it can pry other pieces of rock off of the bedrock and then transport them to other locations. So ice flow can transport rocks, in some cases, a very long way in Antarctica. And then as the ice thins, it can leave behind those rocks in a new mountain range in another location. So we agree, okay, I hope I've convinced you, that glacial deposits are telling us that, hey, Antarctica used to be bigger. In some past climate, past time, Antarctica was larger. But what we really want to know is exactly when. It's one thing to say that the ice sheet, yes, it has been bigger in the past, but it's more useful to say when was it bigger in the past and how quickly did it retreat from that high point. And this is not at all a new idea. So a scientist named John Mercer, he visited some of the locations that we have mapped in the past. And he quoted in a 1968 paper, we must await the ability to date these deposits. We must await absolute dating. So he described different glacial deposits and knew that at some point we would be able to assign an age to all of these rocks that glaciers have left behind. And I include this picture in the background. That is a former camp from a mid-60s field campaign that was left behind in a different time, let's say. The environmental regulations would not allow that to happen now. Okay, can we date glacial deposits? As it turns out, absolutely. We can date glacial deposits. And to do so, we rely on cosmic rays. What is a cosmic ray? It is a very high energy subatomic particle They arrive at the top of Earth's atmosphere and interact with molecules in the atmosphere, nitrogen, oxygen, and those secondary particles, some of them are so high energy that they can penetrate through rock. They are passing through buildings right now. We are all being bombarded by the cosmic ray flux. And those cosmic rays can change the atomic composition of existing rock at the surface. So the key to this from a glacial perspective is that thick glacier ice can shield rock from the cosmic ray flux. So when a rock is covered by ice, it is not being bombarded by cosmic rays to a significant degree, but as the ice leaves a location, it is suddenly exposing itself, exposing the rock beneath to the cosmic ray flux. And the cosmic ray flux produces special cosmogenic nuclides that most of which stay within the mineral lattice, the crystal lattice of the mineral, and accumulate there over time. So we refer to this process of basically the breaking apart of molecules by high energy particles as spallation. They basically break apart and produce additional subatomic particles. So here, if you have basically a proton arriving and interacting with a oxygen atom in the atmosphere, that oxygen atom in the atmosphere is going to break apart as a result of that impact and produce other molecules. And so when some of those secondary cosmic rays interact with a rock at the surface, let's say that rock has quartz in it. Quartz is made of silica and oxygen. And when struck by cosmic rays, those oxygen atoms in the mineral lattice can become beryllium atoms. And those beryllium atoms were not in this rock before. The beryllium atoms are not otherwise located in quartz. And so once they are exposed to that rock is exposed to the cosmic ray flux, suddenly beryllium-10 starts to accumulate. So if we look at the periodic table, we have an oxygen atom here in purple that I've outlined in purple, the oxygen on the periodic table. And if it is hit by a highly energetic particle, that energetic particle causes the oxygen atom to break apart. And that oxygen atom then becomes a beryllium-10 atom. So it has to lose 4 protons and 2 neutrons, but it becomes beryllium-10. And beryllium-10 stays inside the quartz crystal and slowly accumulates over time. So the production of beryllium-10 is well known, the rate at which it is produced. That production rate is a function of how high in the atmosphere a sample is, what latitude a sample is, and there's also other cosmogenic nuclides as well. So it's also a function of rock density, the presence of the target nuclei, for example, or nuclide. But for this purposes, we'll focus on beryllium-10. There are other cosmogenic nuclides that can be used for this purpose. But for now, we'll focus on beryllium-10. It has a half-life of 1.5 million years, beryllium-10 does. And so it is useful, actually, for dating things that have happened over thousands of years. For example, ice sheet retreat and advance. So let's review. How can we study the history of the Antarctic response to climate change? We can use glacial deposits. First of all, the rock emerges as the ice thins around the mountainside, and that rock is exposed to cosmic rays. Once it's exposed to the cosmic ray flux, beryllium-10 begins to accumulate, and eventually we collect the rock as part of our research. Once we have the rock, we then isolate the quartz mineral, and then we need to isolate the beryllium-10 atoms in the quartz grains. And then we can see how many beryllium-10 atoms there are and use a production rate to determine how long that rock has been exposed. So once we have the concentration of nuclides, that can take actually a very long time. That laboratory chemistry can take a while. We can then calculate the exposure age. And we can suddenly, all of those rocks that we were finding around Antarctica become useful. They're like clocks that tell us when the ice sheet left that elevation. So I'm going to start with a nice picture. And then after this slide, I'm going to show you a terrible drawing that I made. So I need you to remember this picture when you have to go to the drawing that I made. So this is an undergraduate student who worked in Antarctica with me in 2014, 2015. And we are basically walking down a mountainside. And you can see all of these sort of mismatched rocks. These are all glacial erratics. And we collected rocks down this mountainside to get a timeline of how quickly the ice retreated. So here's the bad picture designed to illustrate this situation. So I made you a little cartoon here. So this is the mountainside, this brown line. And each of these rocks represents a glacial erratic that we might collect as part of our studies. Even though in order for us to get a cosmogenic nuclide concentration, we have to pick up the rock, take the rock back to the research station. The rock has to get on a boat. The boat makes it back to the United States. And then there's a few months of laboratory work to allow us to isolate the nuclide. But for the purposes of this drawing, let's say that I have a special sensor, and the sensor can just be pointed at the rock. It's just going to tell me, okay, this is how many cosmogenic nuclides you have. So let's say that this top rock has 15,000 years worth of beryllium-10, worth of cosmogenic nuclides. We measured the concentration, we know what the production rate is, and we learned that, wow, it would take 15,000 years to produce that concentration. So what have we learned about the ice sheet if this has 15,000 years of cosmogenic nuclides? I know I've been talking for a while, so it's hard to transition into thinking about how you might respond. But what have I learned about the ice sheet if that top rock has a concentration of beryllium-10 that took 15,000 years to generate? What have I learned about the ice sheet?
So presumably that's been exposed for 15,000 years, I would guess, right?
Yeah, exactly.
Yeah,
And
right.
put another way, that's where the ice sheet surface was 15,000 years ago. So thanks, Mason. That's exactly right. That, like, basically the ice sheet left that location 15,000 years ago. And so continuing on with my terrible cartoon here, if you would imagine, okay, it was here 15,000 years ago. What have we learned about the lower rocks? We would hypothesize that they would have younger ages, younger exposure ages, so lower concentrations of those cosmogenic nuclides. And so what we've learned is that these mountains with all of their rocks have basically provide us with a timeline. They provide us with these records of ice sheet thinning. And so this is just obviously a little cartoonish version, but it can basically, the mountains serve as dipsticks, if you will, as the ice retreats down the sort of the edge of the mountain. And my zoom diagram's not very good here. But it's basically giving us a history, a timeline. So just to give you kind of some images from the field here, in this image here, we have an ice surface about 20 meters above sea level. Our highest sample was about 175 meters above sea level. And what we learned from our ages is that a thinning rate of less than 1 centimeter per year over 20,000 years. So we can take basically how much did the ice lower, and we use our series of ages to develop a thinning rate of less than 1 centimeter per year. In another location, we have our highest sample about 300 meters above sea level, ice surface about 75 meters above sea level, and we get, again, a thinning rate of about 1 centimeter per year over 17,000 years. So we want to know the history of Antarctic ice sheet retreat. We're getting, on the order of centimeters per year of retreat. In some locations, some studies, you might get 4 to 5 centimeters per year, but generally speaking, on the order of centimeters per year since what's often termed the last glacial maximum, about 20,000 or 17,000 years ago. So one of the example studies this is a common application in Antarctica, but we basically talk about, okay, what does this mean for the region? So I don't expect you to read that abstract, but just to give you an idea of what, the type of things that we can study. So we visited multiple glaciers to build these chronologies, and we constructed ice surface lowering histories. And we produced graphs that look like this. So very, very simple. We have, in this case, we were using carbon-14, cosmogenically produced carbon-14. And we have basically elevation on the y-axis, the concentration of those atoms on the x-axis, and you can see basically a decline in concentration with elevation. So lower elevation, lower concentration. And these dashed lines here, shown their ages shown at the top. The dashed lines are showing approximate ages, exposure ages, how long it would take to accumulate that much, those concentrations of cosmogenic nuclides. And so a very typical relationship is basically an elevation concentration or elevation age relationship, where we have decreasing age with decreasing elevation. And these dashed lines here are showing where the local ice surface was. So you can get a regional, basically ice thinning rates. Again, typically on the order of about a centimeter per year. What does this mean? Well, most surface exposure age studies thinning rates of 1 to 5 centimeters per year over thousands of years. Today, with satellites, we observe change of meters per year in some places. So, 2 orders of magnitude larger. So if you look at this map here, generated and published in a paper by Ben Smith et al., the dark red areas are showing basically, anywhere from 1 up to 3 up to 6 meters per year of ice thinning in coastal areas. So we're seeing a modern ice thinning rate that dramatically, 2 orders of magnitude, exceeds the historical ice thinning rate. And so it's those comparisons that our cosmogenic nuclide studies allow us to make, to provide basically a long-term context for more recent change. So next up, our project is to drill and collect rock samples from beneath the ice sheet. Ice sheet models predict that parts of East Antarctica collapsed and melted away the last time that CO2 levels were as high as they are today. And so we want to understand, did Antarctica, the last time in Earth's history CO2 levels were this high, did Antarctica melt more substantially than it has so far? So in order to do that, we want to drill through the ice and collect bedrock underneath it to see if there are cosmogenic nuclides that have been generated there, that have lasted over the last 3 million years, that were exposed a long time ago when potentially the ice sheet collapsed due to high CO2, high temperatures. So that is an upcoming project, we hope. And again, but still using cosmogenic nuclides, just those that have been, that are in rock that are currently buried beneath the ice. So I'm sure that generated a lot of questions. I wanted to leave enough time for any questions or things you wanted me to go back to. So I'll leave it there, and I look forward to hearing from you all. Thanks, Mason.
Will there be a difference between the Antarctica portion on the New Zealand side and on the Argentina side?
Yes, there are differences. Let me go basically, well, we can use this here. So the Argentina-Chilean side, the Antarctic Peninsula, is an area where you have a lot of mountain glaciers that's basically kind of emerging from a kind of a spine of mountains that go along the Antarctic Peninsula. And so this peninsula area has a different sort of glaciological context than we have when we do things closer to the interior of the ice sheet. Nevertheless, you can see there's still significant ice sheet retreat, or recent thinning along the Antarctic Peninsula. So they would be slightly different signals because they are glaciologically so different. The most recent areas we've been to are really sort of looking at the tracking change of the ice sheet as a whole, whereas the Antarctic Peninsula has more discrete glaciers that may be responding differently. So I've never actually worked on the Antarctic Peninsula. I do know that they're retreating, but I don't know their long-term thinning rates as I do in other parts of the continent.
Well, I had a couple questions.
Yeah.
That was great. Yeah, that was a really interesting talk. Thank you very much. So So I guess you're using cosmic rays to generate these nuclides in the silica, basically in the rock. So what I guess do you have a sense for what the attenuation constant of those is in the liquid water? Because I guess that would effectively be a kind of like resolution for the measurement.
Yes. So it depends on, so basically you mean like attenuation in the ice. Is that sort of what you
Yeah, right. Attenuation in the
Yeah.
yes.
So generally speaking, we think of the a meter, a meter of ice is sufficient to shield from the cosmic ray flux. And so when we're thinking about changes on the order of, tens or hundreds of meters, that is sort of the type of resolution that we're talking about.
Okay. Yeah, that makes sense. Thanks.
Yeah. And we also, it's actually the attenuation piece is really important. So when we're sampling, we want to make sure we have we want to sample the top of the rock. And that has all kinds of interesting implications. So for example, if you have a place where there's a high weathering rate, if a lot of the accumulated isotopes or nuclides have weathered away and you don't know that, you may be basically farther down the attenuation curve than you expect, and you would get a younger age than would actually reflect the process. So we have to make sure that
Oh, that's right. Yeah.
yeah, it's cool. So you have to make sure you're sampling a preserved surface. And the other piece is if you're sampling a glacial erratic, so we can also do this process in bedrock. That's a little bit of a different, there's some different considerations there, but we measure cosmogenic nuclides in bedrock. But if we think about measuring a erratic from a moraine, let's say, or an erratic stranded on a hillside, we want to make sure it hasn't rolled, for example. So let's say it
Right.
hung out for 10,000 years and then, rolled turned over, and we pick it up and we are only capturing, the top part of the rock for the last 5,000 years or something. That also makes a difference. So you think about kind of sample thickness, you're looking for geomorphically stable landforms if you're collecting erratics. And you want to avoid, for example, areas where snow accumulates. So it's interesting because you're totally
Sure.
right that we call it shielding, but there's any number of things that can shield the
Yeah.
rock from the cosmic ray flux.
Makes sense. Yeah. Thank you.
Yeah, thank you for your question. I appreciate it.
Are there any other metals or any other elements detected in the rocks?
Yes. So, I mean, in terms of cosmogenic nuclides, the study I showed you is using carbon-14 in quartz. That can actually be useful because it has a really short half-life. So it basically, if the rock was eroded, deposited somewhere, left exposed for a period of time, it accumulates some cosmogenic nuclides, and then it's picked up and put somewhere else. You have a chance of some of the previous history of exposure decaying away before basically the clock can be reset, if you will, for a nuclide that has a short half-life. And so C14 can be also useful in bedrock dating because if a mountainside is covered by ice and then the ice retreats and it's covered by ice again and the ice retreats, for long-lived nuclides like beryllium-10, you can constrain the total period of exposure or burial if you use 2 nuclides. But for C14, if you collect a sample and you measure C14 in it, because of the short half-life, you're more likely to capture just the most recent exposure. So that's a lot of words coming out of me, but we do measure, we measure stable isotopes too. So sometimes neon 21, chlorine 36 is another. So there are a lot of different cosmogenic nuclides. It depends on which minerals present, what time period you're interested in, and you often measure 2 because, for example, if the production rate's similar but the decay rates are different, you can use 2 nuclides to say more about how long the rock has been buried and exposed, because you're then looking at kind of the nuclide pair and seeing, oh, well, there's only a sort of a limited amount of burial and exposure that can produce those 2 concentrations together.
Mm-hmm. Thank you.
I had one more thing. I mean, I'm sorry, something's going on with my video here, but so do we have a good sense that basically the cosmic ray flux has stayed relatively constant over the time periods of which you're doing these measurements in order to kind of make sure to you know, or that we have an independent record of that we can kind of normalize out for these, or?
That's a really good question. So there is variation in the cosmic ray flux on the solar cycle, but those variations are pretty small. They're basically within the noise of they're within kind of the errors that are associated with our calculations anyway.
Okay.
And so over the frankly geologically relatively short actually time periods that we're looking at geologically, yes,
15,000 years, right? Okay.
yeah. We assume the cosmic ray flux has been pretty stable. But that's, which is not to say exactly the same. It's just to say that the variations that happen, like the 11-year solar cycle or other cycles, those changes are small enough. Those fluctuations are small enough that they are not. They're sort of within the error inherent in these measurements anyway.
Okay, makes sense. Thank you.
Yeah, great question.
How do the data from the Arctic side, the north side, compare with this Antarctic side? Both are roughly the same as far as erosion is concerned or melting is concerned, or are they different? Do you have any data on the Arctic side or from literature?
So you mean comparing the sort of the Arctic to the Antarctic?
Yeah.
So people who do this sort of work in the Arctic are mostly focused on Greenland. Sort of our, the Earth's other ice sheet. Although there is some mountain glacier work, there's some sort of smaller scale glaciation work where cosmogenic nuclides are also done to track the history of ice retreat. And in Greenland, I mean, they are slightly different. Depending on where you are in the continent, you're going to get slightly different histories. But generally speaking, we see acceleration of mass loss from the ice sheet in more recent years. And very roughly kind of retreat from a maximum that occurred 18 to 20 something thousand years ago. So it's still a broad range, but sort of the last glacial maximum is sort of a global signal. And there was a last glacial maximum in Greenland from which the ice sheet has been retreating for thousands of years, but at a rate much slower than what we see today.
What will be your message to the high school students or undergraduates who are much concerned about this climate change and all that? Do you think that by regulating the emission of these gases and the other pollutants, we can actually bring back a little more ice sheet?
Well, I think perhaps that would not necessarily be my goal to, I think the ice sheet change is in process. The retreat, the glaciological retreat is in process. And so perhaps I think what I would encourage students now to do is to learn as much as they can and to think about ways that we can adapt and become more resilient in the face of these changes. So for example, what support will coastal communities need? And how are we going to help those communities adapt or even migrate? Or if we are, for example, in Southern California, right, we see lots of different impacts from climate change, extreme weather, wildfires, right? And so what does it take for communities to be resilient in the face of those challenges? Which is not to say that we should not consider ways to address the greenhouse gas emissions that you refer to. We should. But while we are doing that, we should also think about ways to make our communities more resilient in the face of changes that are already in process. And the glaciological changes that we're seeing are pretty hard to turn back. That takes a global climatic shift that would be quite challenging to engineer. But I think just an awareness of the challenges that coastal communities will be facing, and how can communities, how can we support communities that are going to be facing flooding and relocation?
Thank you very much.
Yeah, thank you. Yeah. I will stop my share now. I don't think anyone needs to see my slides anymore. Hold on, Okay.
So if there are no further questions, it's a great talk, actually, a great educational talk, actually, as to what is happening to us and how we can actually at least try to keep it at that level instead of going down much further, especially to the coastal areas you are talking about, because I also live in Torrance, so which is very close to the
Yes,
sea.
yes.
So we need to be very careful about these things, I presume. And thank you very much for a very scintillating and very informative talk, Claire. And hope when we circulate this to all our schools and maybe some at the national level also, there will be a little more information, a little bit more awakening about what is happening to the coastal areas.
Yeah, well, then I'm happy. I dropped my email in the chat, so if anyone wants to reach out, I realize that won't be on the recording, but I'm certainly happy to connect with classrooms or people who are interested in this work. And I'm just one person, but there's many people who do this work, and happy to also connect folks about things that others know more about. So yeah, don't be shy about reaching out again. But I was proud to be part of this event. So thank you so much for the invitation. I really enjoyed talking with you all today.
Thank you.
Yes.
Bye then. Thank you.
Bye. Thank you.
Bye.
Thank you. Bye.